We're actually starting the presentation now. And I think that you probably all are familiar with a very famous physicist called Richard Feynman. And he was also a funny guy. And, he was a very original guy. He was drumming in nightclubs, um, funny and interesting individual. And one day he said, listen, guys, I have the equation that solves all the problems of the world. It's called U equals zero. And it's actually all the physics is in this equation. And if you solve this equation, then you can know anything about anything, quantum mechanics, solid state, mechanics, electricity, anything. But then people asked him, okay, so what does that U look like? And he said, this is how U looks like. And all we need to do is to take U to zero. And I hope that it rings a bell um, to you, because what we are seeing here is something very similar to what?
It's an Hamiltonian.
No, no. We're seeing something very similar to the least square loss function. You're taking many, many square things, and you take their sum to zero. And if U is equal to zero, then F must be equal to MA, and V must be equal to IR, and E must be equal to MC squared. So this is, in a way, a universal equation. Okay, today's lesson, I mentioned a few words about the XOR network. As I said, if one of you would like to solve the XOR network by just working with one of the libraries, be my guest, and perhaps before the end of the lesson, share the screen and we'll discuss the results together. So I'm going to talk a little bit also about matrix multiplication and fully connected networks. We're going to do this very briefly. And then we're going to divert a little bit to a non-mathematical scientific thing and tell you about a very interesting person called Jensen Huang, who was the founder of NVIDIA. And we can see how his story is very strongly related to many of the things we've discussed in the first lessons. And then what we'll do, which is the most important thing of the lesson, is we'll solve a real problem, a digit recognition problem, with the ML models. And we'll just go through all the details on how it's done. And by the end of the day, you will know how to solve ML problems or AI problems by yourselves very easily. And then towards the end of the lesson, we're going to discuss the exercises. Okay, so we talked about the XOR. I don't think we need to delve deeper. If there are questions, we can talk about it perhaps towards the end of the lesson. And we're actually starting now. So just to remind everyone, the most important action in linear algebra is matrix multiplication. I think I explained in lecture number 3 why specifically this method of multiplication was chosen. And what I showed is that this method preserves linearity. And just, for those of you who do not remember, I'm multiplying A times B. So first of all, the number of columns in this matrix has to be equal to the number of rows. So 3 and 3. And obviously, let's just show this very quickly. The 28, this one, the 1, 1 is just, is just this times this. Okay, you can see 1 times 6, 2 times 5, 3 times 4, and we get 28. Okay? Let's show this a little bit more formally. In order to multiply two matrices, you have to have, as I said, the number of rows, the number of columns in the first matrix to be equal to the number of rows in the second one. Otherwise, you cannot multiply them, okay? So these two always have to be equal, always. Otherwise, you cannot multiply it. But I would like to speak about a very special B matrix here. And this is when P equals 1, okay? So what happens to B if this is a 1? Can someone tell me? It's a vector, okay? If you have n on 1, you have a vector, one of these animals that we see a lot in physics, and you also had it in your exercise. This is a vector. And you see we have one column, this is 1, and we have many rows, which is the number of sites here. So what you see from this equation is whenever you multiply a vector by a matrix, you have to get a vector because P equals 1. But interestingly, the vector can change in its size. So let's just give a very quick example. Let's say that M is 5. Let's say that we have 5, 5 on 4. So this matrix is 5 on 4. This here must be 4, right? 4 on 1, because this is a vector. And the answer, even though this was 4 on 1, the answer will be 5 on 1. So what happened? The vector became longer. Of course, we can also make it shorter. And when M equals N, in other words, when A is a square matrix, the vector will stay the same length. And that's usually the vectors that we use in physics. Again, it's going to be used extensively in the exercise. And just to remind you, if you have a vector, you multiply by a matrix, something happens to the vector. It will still, if it was a 3D vector, it will stay 3D vector, but generally it will change in its length and in its direction. However, when we talk about machine learning, these matrices are usually not square matrices. And I would like to explain why. Sorry. So I want to share with you an interesting chat I had with ChatGPT, which I prepared for you. And of course, I will send it to you by the end of the lesson. Okay. So this is what I asked ChatGPT to do for us. Assume that I have a fully connected artificial neural network with the following features. So I just invented the network. I have 3 input nodes. I have 2 hidden layers, 2 and 4 neurons respectively, and 2 output neurons. So the network will look something like this. I also asked it, see if I have a drawing of this network. Yeah, okay. So I even asked it to draw the network. And this is how the network looks. And what you see here is that I have, is that I have 3 inputs. Here I have a hidden layer of 2, another hidden layer of 4, and the output layer is 2. Now, what I want to do is I want to connect this, I want to calculate this layer using matrix multiplication. So let's try to see. First of all, we have a vector here, which is a 3 vector. It has 3 elements, right? Now the matrix will have to be a 2-on-3 matrix, because first of all, in terms of the number of weights, each one of these has 3, and we have 2 of them. So we have to have, 2-on-3 matrix, which will have 6 elements. What I would like to show is that if I multiply this matrix, this 2-on-3 matrix, by this vector, I will get this vector. And by the way, it's not very surprising. Think about it. We have a 2-on-3 and then 3-on-1. So the result should be 2-on-1. Let's look at it more in details for a minute. I even asked it to do the calculations for us. So what you see here is that we have a matrix of 2-on-3, which multiplies a vector of 3-on-1, and of course we get on 2-on-1. But if you remember, we still have an activation function. So we just what we did now, we just accumulated the weights times the inputs. But now we have to have, a ReLU or a sigmoid or a John the neuron, whatever. We have to have an activation function. And after we finish that, we go to the next layer and the next layer. So basically, the calculation that we get is this is the output. In order to get to the output, what you have to do is to take the input, which is a vector of 3, in our case, multiply it by this matrix, add the B, activate the activation function, and you have this one. Now, whatever you got, multiply it by the second matrix and add the B, and then multiply it again and add the B. So what I want to show is that the whole feed-forward process is really, in a way, a combination of matrix multiplication. But what I want to do here, and also respond to a nice question that was asked last time, why is it so important that the activation function will not be linear? And this, I want to explain it in a very nice way. So what I told ChatGPT is to assume for a minute that all the B's are zero. B1, B2, and B3 are zero. The reason you can assume it is because there is a very nice trick to absorb the B's in the weights. There's a very nice trick that if you add to each vector, each layer, an element that is equal to 1, it's equivalent to doing a B, and I'll be happy to explain it towards the end of the lesson. It's very, very simple. But you have to believe me at this stage that we can very easily put all the B's to 0. And then what I asked our friend ChatGPT is to tell me what will happen in this case when the activation functions are linear. So our friend did a calculation, and he said, what you will get really is a multiplication of the three W's, of the three matrices that really define the network, okay? I want to remind you, okay? This was the formula. We put all the B's to 0, and then we took all the activation functions and, have them linear function, 5, 1, 7, it doesn't matter. But what you will get is simply a multiplication of the matrices. Now, this is really crazy because if let's assume that you have 10 matrices like that. Well, if this is the case, all of the multiplication of this tree is actually one matrix. Okay, in our case, it will be a 3-on-2 matrix, which is a multiplication of all the three matrices. And what it means is something very interesting, that the number of parameters is going to be very small because everything is dissolved into the effective matrix. So if you can take 4 matrices, which are big matrices and have many weights, and instead of all of them put a smaller matrix, it doesn't make sense. It means that you lost all the wealth and the richness of the network. And this is why I wanted to show you visually why you can never get rid of these. Why you don't want to get rid of all these unlinear functions, because as I said, the network will become extremely degenerate and small. What I did here, and I'm going to send you the whole thing, is I actually asked ChatGPT to take a numerical example. So you see, these are the 3 inputs. That's the first matrix, and after you multiply them, these are the B's, and it did all the calculations for us. And maybe I'll just show one line. So this is the first line. If you remember, we multiplied the 2 on 3 times 3 on 1. And what we got as a result is 3.4 and minus 0.3. But we also have an activation function to worry about. This is just the result of the matrix multiplication. But if you remember, after we add everything, we have to do an unlinear activation function. In this case, it's a ReLU. Now, what ReLU does, if you remember, is everything that is under 0, it will just put a 0. Otherwise, it will put the number itself. So obviously, we get 3.4 and a 0 here, which is exactly the John the neuron activation function, if you remember, with bias, which is 0. And here we did the complete calculation. The last output layer, we got this result. Because we used ReLU, this becomes a 0, and that's the final answer. That's the result of the feed forward of all these multiplications. And what I did at the end, and it's something that is fun and nice that I urge you to do, is I told ChatGPT, look, I just created the network. Can you invent a problem for it? So it invented a problem, but then I said, the problem is not really that interesting. Can you suggest a more fun and funny problem to solve? And then ChatGPT invented, actually a not so funny idea, but cute. And what I would urge you to do as the next step is tell ChatGPT, okay, very good. Now solve it for me. Now just write a model and solve the problem that you invented, that I invented. Okay, now the reason I went through all this is actually to shed a few light about a very interesting person called Jensen Huang, who is the founder of NVIDIA. What we've learned here is that in order to do feed forward, training, backpropagation, you have to have a lot of matrix multiplication. It's critical. Now, the story with Jensen Huang is really an amazing story. So he was born in Taiwan. I think his mother was a teacher, his father was an engineer. And then at some point of time, his family emigrated to United States, I think to Washington State. He was a very good student, but he had to work as a dishwasher, sorry, in a restaurant in order to make a living. And he started a company called NVIDIA, and it was a fledgling company. It was really doing very bad. He almost had to shut down the company a few times. And in 1999, I think it's either him or one of his co-founders had a brilliant ideas. In 1999, the gaming industry was on the rise, especially some games that Microsoft developed at the time. And if you remember, I told you in the third lecture that one of the things you do with matrices is you do rotation. You rotate vectors. There's a very interesting matrix, an orthogonal matrix, which is called the rotation matrix. And what this matrix does is simply when you multiply it by a vector, it just rotates the vector. It preserves the length of the vector, but it rotates it. Now, obviously, in order to do 3D manipulations in gaming and to do it fast, you have to have a lot of matrix multiplications. And here came the brilliant idea from the NVIDIA leading team. What they said is the following: why don't we build a chip, a special hardware chip that does a lot of parallel calculations, especially for matrix multiplication? Now, if you remember, when we multiply a matrix, we multiply this by this, and then this by that, and then this by that. And what they said, let's do them all in parallel, and we'll save a lot of time. And this way, we'll be able to do 3D manipulations much better, and it will help a lot the gaming industry. And that was a bit of a lifetime. It was, as I said, in 1999, the company was in dire straits, as we say. And then NVIDIA started to grow because the gaming industry started to adopt the chips, and more computers, especially gamers, started to build their own computers with NVIDIA GPUs, graphic processing unit. And that was 1999. And as I said, it really helped NVIDIA grow and develop, but it was still an average company in size. Around 2013 or 14, I think I mentioned once a very famous person in the AI industry called Geoffrey Hinton, a Nobel Prize winner and Turing Prize winner, and he's considered the godfather of AI. One of his students had a good idea. He said, why don't we take the GPUs that were actually developed for gaming and use them to train networks? Because I just showed you that working with neural networks, especially fully connected networks, is just a bunch of matrix multiplication. Everything here is matrix multiplication. Everything. I mean, the word TensorFlow, tensor is really a matrix. More than a two-dimensional matrix usually. So it's all about multiplying matrices.
Can I ask a question?
Sure.
Why use GPU instead of CPU? Why the standard CPU is not fitted to this assignment?
It's a good question, because the standard CPU does many things that a GPU cannot do. But what it doesn't do is it doesn't multiply matrices fast enough, because it doesn't have the parallel mechanism to do matrix multiplication. So, some companies try to join together the CPUs and the GPUs, but basically what the first GPUs did, their expertise was just multiplying matrices very fast. And they did it by using a lot of parallel work. Now, I don't know if we talked about it in the past, but there was always a battle between two AI camps in the Silicon Valley. Some of them were doing symbolic, and I will explain in a minute what is symbolic, and other ones were doing neural network. Geoffrey Hinton was the person that said, we have to solve problems by neural networks because our brain is a neural network, so let's not try to be smarter than our own brain. The other camp said, no, we don't have to be like our brain, let's invent something different. So I'll give you an example in face recognition. So in the old days, how did they recognize faces? They would look for the eyes and for the nostrils and for the mouth and make all the calculations. And then, for each person, they had a sort of a database that sort of defines the facial characteristics. What neural networks, obviously, we don't do that. I mean, when we look at someone, we don't start to measure the distance between their nostrils. We do something different. We take the picture that we see and just feed it into a network. And Geoffrey Hinton said that this is the way we should work, not to do the symbolic AI. And every year there was a contest in Silicon Valley where people try to to recognize as many pictures as possible. And Geoffrey Hinton's team always lost to the people that were doing symbolic. And apparently, the reason they lost is because they were not able to build networks that were big enough. And Geoffrey Hinton knew it, but there was nothing he could do about it until in 2013 or 14, I'm not sure about the year, one of Geoffrey's engineer, I think his name was Alex something, Lishansky or something like that, said, hey, I can take one of the NVIDIA GPUs that were actually designed to do gaming, and since I'm a good assembler programmer, I will just, reprogram it to do matrix multiplication. And this way we'll be able to do bigger network and faster networks, and maybe we'll do better in the next contest. And that's exactly what he did. And in that context, they won #1 by far. And the beautiful thing here is that their victory was so clear that the other camp, the symbolic people, left their pen and pencils and said, that's it, we lost the battle, we're joining you. It was such a clear victory. So what you saw here is that this person that was washing dishes in restaurants created a $2 trillion company by just a few brilliant ideas. And I want to show you something that may not be related. First of all, I want to show you a very interesting interview with him. And please listen carefully to what he says.
Going back to that question, what kids should study in the future?
Do you hear the audio? Okay.
This is what Jensen said.
If I were starting all over again, I would realize one thing, that one of the most complex fields of science is the understanding of biology, human biology. Not only is it complicated because it's so diverse, so complicated, so hard to understand, living and breathing, it is also incredibly impactful. Complicated.
So basically what he says, and you can see it in the beginning of the video, is don't study computer science. So what he's suggesting to the young generation is study science, study physics, study biology. This is where the future is. And that's pretty amazing from the person that almost single-handedly exploded the whole AI industry. Any questions so far? Okay, so by the way, as always, I'm going to send you the presentation, the deck. You'll be able to see all the movies, and also all the links that have a turquoise color are links to simulations that you can obviously work with yourselves after.
Going back to that question.
Okay. Now,
Joshua, I have a question. Are you agree with this statement about learning science as physics and biology nowadays
absolutely.
instead of
Absolutely.
computer science?
Absolutely. I can tell you, and you will see it when we get to the exercise. In the old days when ChatGPT just started, I tried to explain it to my friends, and I said, assuming that you have a genius in programming sitting next to you, he or she have all the patience in the world. You can ask stupid questions. Nobody will make fun of you. And again, I think you know that I was in the high-tech business for 35 years. So you always have in every company, we call them the nonlinear people. You know, a genius that can do something in one day that other people would do in a year. And I'm not exaggerating. You know, I've people like that have worked for me in the past. So imagine someone like this sitting next to you and just working with you on everything that you want. But what I have learned to say in the last few weeks and months is that it's not only that. Imagine that you have Paul Dirac or Richard Feynman or Einstein sitting next to you and helping you with the research. So what is happening today with LLMs is that they don't only help you with programming, they help you with science. They help you to they help to help you with science intuition, with physics intuition. They are creative. And I'll actually show examples that stunned me. When I prepared the exercise for you, while I was doing, I was really stunned. But by the dialogue I had with one of, I think it was ChatGPT or Claude, I'm not sure. So to answer your question, I absolutely agree. By the way, I don't think it's wrong to study computer science. I think a lot of good computer science will always be needed. But I think that the big magic is going to happen in biology and physics. Because everyone today not only has someone that will help with programming, but someone that will help with thinking. This is huge. I mean, never in the history of humanity we had something even close to that. So I want to show again a simulation, a movie that I showed in the past, and explain how it's so nicely connected to Jensen Huang. Let's go to it. I want you to remember what you just saw, that these few seconds, because we'll get to them in a second, okay?
It's almost like they acted like one brain of sort.
It's a good point. Yes, it's a very good point. I want to show it again because I'm going to ask, just try to remember what you're seeing here. Okay, let's continue now. And if you remember, I showed you a simulation of the birds, but I also showed two. What I did is I took two simulations with the same initial conditions. And as you see, the first side and the right and left side are completely equal. But then I wanted to take two very different extreme environments. In this environment, the birds want to be together. They're very tight. And in this environment, they're completely random. Okay, so what you saw in the movie is somewhere in the middle. This is where the magic happens. It's called the edge. It's called the edge of chaos or an emergent situation. Now, I think I told you before that if you take one of these birds now and just take it out, nothing will happen. It will still be random. The same thing here. But if you take the original one, the one that is somewhere in the edge of chaos, moving one bird will eventually change the behavior of the whole thing. So you will see completely different patterns. And one way to explain this beauty is if you had to ask someone to describe what they see here, they'll say just, a black bulb moving together. And if you ask them what you see here, they'll say something random. But if you will ask someone to describe what you saw in the movie, they will never be able to explain it in one word, or two words, or one sentence. Now, it may be funny, but that's almost a scientific way of proving that this area in between is such a special area. And we'll also see it in the exercise in a few minutes. The reason this is so strongly related to Jensen is because if Jensen were here, a genius, a creative genius like him were here, nothing would happen. So if you were in a very tight hierarchical society, like the Middle Ages, nothing would happen because there's no communication. Now, in the Middle Ages, they had some activities, they had wars, but what really happened is one black bulb like this interacted with another black bulb and they killed each other, but nothing really interesting happened. Now, if Jensen Huang lived in a world of complete anarchy, also nothing would have happened. In order for big things to happen, the special individuals have to be in the situation in between, which you saw in the movie. So what I'm trying to say is that we're all fortunate to live at the time of history, which is an emergent time. And in a time like this, a brilliant individual or event can change the world. I mean, one example of an event is Me Too. Think about it. A few years ago, something terrible happened in Los Angeles. A few days later, it sort of propagated to the whole world. That can only happen when you're in an in-between situation, not in anarchy and not in stagnation. Okay, so let's continue now, unless you have any questions. And we'll get to the tachlis, and that is training models. So now what we'll do now is we'll take a very interesting problem. We're going to build a model that detects handwritten digits. So before we actually start the work, I want to remind you actually something that we said in the last lesson. When you build a model, you have to think about inputs and outputs. What's the input and what's the output? You have to select the architecture. You have to think about the number of parameters. You have to choose the activations, and you have to choose the loss function. Now, that's actually not very true, because when you ask the model, the LLM, ChatGPT or Grok or Claude, to build something, they will, please listen very carefully, they will do all this for you. They will decide on what the architecture should be and they're not always optimal and they're not always right, but at least it's something to start with. So you now can go to an LLM and say, build a network that solves XOR, and that's it. And it will build a network and it will make all these decisions for you. And just to remind you what output and input means, so in the XOR problem, we had 2 inputs and 1 output. So that was the black box. And then, we decided we tried to do a perceptron. Nah, it didn't work. Then we built this network, which worked, but we could have built this network, which would probably work much better and quicker. So that was the XOR problem. And then we looked at another problem, the yellow magazine. So if you remember, we had 3 inputs. Here we had the salary and the bonus, and then we just created the network in between. And by the way, the movement between here and here is just a matrix multiplication. So here we have a matrix of 3 on 5. Here we have a 5 on 5, another 5 on 5, and this one is 5 on 2. So all we're doing is multiplying matrices and executing the activation function. That's all we do. And then we took another example, of the mole detector. Remember when we copied the brain of the best dermatologist? So this was the input, this was the output. We prepared the input in a better way. We made it a 64 points vector, and then we started to create the network. And what we're going to do now is something very similar. We're going to take a digit that was handwritten and try to guess what it was. Is it a 7? Is it a 4? Is it a 9, etc.? Okay? Of course, also with the digit, as you can see, we made it into a vector. These digits are usually 28 by 28, so the vector is 784. And what you have actually is a network where on the left side you have a vector of 7084, and on the right side you have a vector of 10. And all you need to do is try to guess the number here, which one does it affiliate with on the right side? And of course, now you build a network. So this is a fully connected network. We'll build one like this in a few minutes. I just want to tell you that there are other architectures. There's an architecture which is called CNN, which we'll also learn, which solves the same problem. It also has weights and biases, but the weights and biases are arranged in a very different way. It's not in layers like that. It's very, very different. But again, the same idea here. Here you have the input, here you have the output, and what you do is tweak the weights and biases to get the right answer, to minimize the loss function. Okay? So let's start with a quick demo, just for you to understand what we're trying to achieve. Okay, so what I have here is a way to, a canvas to draw a digit. Let's draw a 1, and I'll do a classify. And by the way, you have access, of course, to all these simulations. And what you see, let's look at it here. First of all, it did detect that it's a 1. Now, what you see here is what happened to the 1 that I drew when I had to make it 28 by 28. You see it was a little bit pixelized. But here, you see something very interesting. What it told you here is that, yes, it did give 1 a very high chance, but for some reason, it also gave 5 a reasonable chance. So 1 was the winner, which is nice, but it wasn't a knockout victory. Let's do another one. Let's do a 2. Classify. First of all, you see that the model thought it was a 3, and it was extremely confident that it was a 3. Okay, so this model is not really that good. For some reason, the model thought that this thing here is a 3. Now let's go back to the one before. Let's try to do it again. Now it thought it was a 3, and it's interesting why. Because when we did the pixelation, you see this thing was added. And what you see here is that, yeah, it gave 3 a very high chance, but it also gave 1. The reason, by the way, it happened is because of the pixelation. This thing here made the model think that it was a 3. It also gave some probability to 2 and to an 8, which could make sense. Okay? So what you see here is what the model thought about the input. So this is the input, this is the output. Now let's try to think what should be a good loss function here. And I will tell you what we're going to do. We can do mean square also, okay, of course, but the best loss function here is called cross entropy, and I want to explain how we do it. So when I drew this, I knew that it was a 1, right? I meant that it's going to be a 1. So the loss function I'm going to do is go to where the 1 is and calculate the log of this, the log of the entry that I got here. Why log? Because obviously, if this was 1, the log of 1 is 0, which is great. And we always want the loss function to be 0, right? So the way the best loss function for this situation, you can do mean square, it will work well also. But there's a clever way. I mean, I knew, remember, when we do training, we know the right answer. So all I need to do is, okay, I know the right answer. Let's see what number he gave me for this answer. If he gave me 99%, fantastic. I'll do a log and it's going to be a very small number. But if, like here, it gave me, let's say, a 70%, then it seems that we're very bad. Okay, it's not a good number. So we have to continue with the back propagation. Any questions up to here? Okay. So basically what I did now is just explain the problem. What we're trying to do is take a digit that was drawn by someone and try to guess what it is. Now, the very good news is that there's a huge database with 60,000, I think, handwritten digits. And this database, for each image, it also has the right answer. In other words, the label. So they took 60,000 situations where people drew a number and also said what the number was meant to be. So we have 60,000, a huge database of 60,000 images, but each image has a label attached to it. And this label says what the drawer of this digit meant it to be. So what we're going to do basically is take a digit, make it into a vector, move it through a network, and hope that this number was really the biggest one. In other words, that the bigger, out of the 10, the output layer has 10. We just want to make sure that we're going to train the network on and on until every time I put a number here, it will get the right answer here.
So like building a sieve of sort?
Sorry, building?
A sieve of sort, like מסננת.
No, what we're doing here is what we're always doing in machine learning, in supervised learning. We take a bunch of right answers, we take on the left the question and on the right answer. And what we do, we force the network, the weights and the biases, we tweak them in the way that the more we do it, the error will go down and down. So our job is to minimize the loss function. And if you give me a minute, we'll go a little bit deeper into it. So maybe I will answer the question as we go through it. I just want to mention that there's a very nice trick that we do with these systems. It's called softmax. And what softmax does is something really nice. So let's say we just put a number here, we put the vector here, the system started to do the feed forward, and we got here a bunch of numbers. Obviously, you agree with me, you will have to get some numbers here. Now, what you want to do is to normalize the numbers. In other words, to make sure that they sum into one so it will become a probability. And the way you do it is by doing softmax. So what softmax does is it takes a vector and it transforms this vector into a vector, but which is normalized to 1. You see the sum of all these is 1. And this was the bigger one here. And you see now it became 90%. So this is the way softmax works. And we'll go deeper into it when we look at the code. So that's the activation function we choose for the last layer. So obviously in the last layer, we'll get 10 something. We don't even know what the numbers are. But in order for this to prepare it for the test, we softmax it so it becomes a probability. And obviously we just multiply with the digits that we meant. This is another example of softmax. You see, by the way, that if you had negative numbers, since it's e squared, it makes a small positive number out of them. Again, this is just simple. It's something you see a lot in thermodynamics. But basically, what you see here is that you take the output, this is actually the output vector, and you softmax it so it becomes a probability. So all we are doing is just build.
Why normalize like this? This is a weird normalization. Why do that specifically?
Why do you say it's weird? Oh, why didn't we just sum it?
It's not. Yes, it's not the regular way to normalize.
It's a very good
reason.
It's a very good question. Yes, you're right. Is it Yasmin?
Yes.
Okay, what Yasmin is saying, hey, you can normalize things differently. Why? You can just add and divide. So there are two answers. First of all, if we just add them and divide, we have a problem with a minus here. But in addition to that, what you will see that softmax does, it will take the maximum and make it more dramatic. So if you look at the 3 here and 1.75, it's a factor of 2. Look at the factor here. It's more than 2. So this is why softmax was chosen. It has this talent to sort of take the larger number and sort of exaggerate its greatness. And apparently, it gives good results when we put it in a network. But it's a great question. So what I want to show before we do the tachlis, I want to show a movie which is done by an amazing YouTube channel which is called 3 Blue Brown. Are you familiar with that? 3 Brown Blue, I always forget. It's the best ever developed pedagogic channel, I think, in the history of humanity. And you know, if you know, sometimes I think that instead of talking to you, I should just show a movie. So this is one of the movies that I very strongly recommend.
Handwritten digits.
I will send you the link. But what you see here is that we have a 7, okay? This is the vector, which was built out of the 7. And you see the network is running. And since the network is trained, great news. You put a 7 here, and you had a 7 here. By the way, if we would do it before we started the training, probably you would have a 0, 10% on the average of each. I mean, if these numbers were random, then it will not choose the 7. We are making it choose the 7 by reducing the loss function all the time. So this is a movie that I urge you to look at.
This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more and handwritten digits.
Okay, so I very, very strongly recommend that you look at this movie. This guy developed something like 8 movies, which are really gems, also for Transformers, for CNN, for all the architectures. And he also does physics and chemistry and biology. He's really a unique expert in pedagogics. And what I want to show is another beautiful movie, which actually shows it in a way that's more similar to the brain, to the way the brain works. So this is also a trained model, but it looks more like the brain. See, the input is here, the output is here, and you can see that the network is trained because it's always getting the right numbers. Now, the reason I like this because I hope it reminds you the zebrafish movie that I showed you with all the lights going in the brain. And if you remember the glowing of John the neuron, that's exactly what happens here. Every activation is a little light in the neurons. Okay. So this is, again, a trained network. You see a 9 here, and it was able to locate the right 9. And the reason I show it, because it shows how beautifully it resembles a brain, albeit a very primitive brain. This brain can only detect numbers from 0 to 9. That's all it can do. But it's a brain. Remember, last time I showed you a more interesting brain, a brain of a dermatologist, which can detect tumors. Okay, so let's see now how we do this in real life. So I think I explained the problem. I hope you understand it. And let's solve it. So the way we'll solve it, I'll actually go to DeepSeek this time. I decided not to use ChatGPT, just to fool around with DeepSeek. And I want to show you how I created the whole thing, okay? So I told DeepSeek, I'm teaching a beginner's class in ML, and we're all using Jupyter Notebook. The reason that I mentioned it is because I wanted the model to create cells, to work with different cells. Please provide a Python code for a simple MNIST digit recognition solution. Pay attention. I mean, I did not say anything about how many layers. I just told, just build a model, solve the problem. Please use TensorFlow. I explained why. And a fully connected network. The only thing I'm telling the model, I told DeepSeek, use TensorFlow, don't use PyTorch, use TensorFlow. And just make sure it's a fully connected. Don't do transformers or CNN. Just take this architecture because that's what we've learned so far. Additionally, create a second cell. So in the first cell, you solve the network. Additionally, create the second cell, which does the following. Okay, this is really a crazy idea. Have the user input one of the alphabet letters. It's not a mistake, not a number. So what I did here, I told DeepSeek, create a software that asks the user to enter a letter, not a number. And then put the letter in the same format that the numbers of MNIST are being put into. And after that, feed it to the network. So I'm doing something which sounds really stupid. I'm telling it, take the network, the trained network, and instead of giving it numbers, give it letters. And let's see what will happen. Okay? So let's look at the code of this part. So this is the network. I want you to see how amazing it is. Only this cell does the job. And I want us to go almost line by line to understand what we did here. Okay. So first of all, I think you probably all feared, wow, a database of 60,000 images. How am I going to go into this database and start getting all the images? Well, fortunately for us, there is a TensorFlow command which does it. Look at that. TensorFlow keras dataset mnist load data, boom. One command and the whole database of 60,000 was loaded. Look how beautifully everything is abstracted. Nobody wants you now to go to the website. If I had to do this a few years ago, it would take me probably a day to start fetching the numbers from the database, to do it right, to do it in an optimized way. But here, TensorFlow just gave us one command. So now we have the whole thing. So what happened here is we built an Xtrain and an Xtest. And this is a very important opportunity to explain why we need always to take the data and divide it to a train and a test. So what we usually do when we get large amounts of data, we train the data only on 80% or 60 or 70, it doesn't matter. Usually it's 80% of the data. So we do the backpropagation on 80%. And what we do then, we take the other 20% and test it and feed it into the network and see if the test data also gives good results. Okay, sometimes there are problems, overfitting, we'll not go into it. Sometimes you can see a situation where everything works well on the 80%, but when you go to the 20%, something doesn't work. And this means that the network is worthless. Because if the other 20% didn't work well, and I want to remind you, for the other 20%, I have the right answer, so I can immediately know whether it's good or not. If it doesn't go well, then there's no use for me now to try to enter numbers because the network is not working well. It's working well only on the 80%, but who cares? I don't care about the 80%. It's like, imagine when we did the tumor situation with the dermatologist, that we had a system that only gave good results on the tumors that he or she photographed. But then if we give other images, it will not give a good answer. This network is completely unneeded for us. So for that reason, we take the data and we do an Xtrain and Ytrain. X is the input and Y is the output. And we do an Xtest and Ytest. Okay, this is really where it all happens. This command really sort of makes the decision on the network. And let's see what it did. So first of all, what you can see, the word sequential here means that it is going with what we want, the fully connected. So this is the architecture. And then what we're told here is that the input layer, see input, is going to be a flat of 28 on 28, which is 784, okay? So this is defining the input layer. Now there is one hidden layer, and it has 128 neurons, and it's going to do ReLU. That's what the model decided. That's what DeepSeek decided for me. And then the output layer, the final one, is going to have 10. And as we said before, it's going to use softmax. Softmax is that special normalization function that we like. Okay? So look at that. We didn't tell DeepSeek anything. We just told DeepSeek, look, solve the problem. Solve the digit drawing problem. Use TensorFlow. By the way, if I use PyTorch, it would be almost similar. And this is what the model decided. I'm not sure it's a good decision. We'll play around a little bit with it. And here, once we sort of created the model, we have two more important commands. This command is called compiling. It's sort of preparing the whole thing for work. And here, what we're doing is we're defining the loss function. So the loss function that was selected here is called sparse categorical cross entropy. It's basically what I told you before. When we know the real number, we go to the softmax and we just take the log of it. And that's the loss function. That's sparse categorical cross entropy. This is not important. And this command actually runs it. So this command, model fit, actually runs the model. And here you see the number of epochs, the number of backpropagation, which is really, really small. Only 5 times, only 5 iterations we're going to have. And let's see what it does. Let's run it. See, we're going to have 5 epochs. And we see very nicely that the loss towards the end is 0.83, which is not bad. So we started with 0.1, and in 5 epochs, we were able to reduce the loss function. But if you remember, I asked DeepSeek to do something really crazy, and that is to have the user enter a letter from the alphabet and feed the letter into the model, which is a crazy thing to do, unless maybe we take O, which looks like a 0, right? So let's do that. And what you see here, it's just taking the number for me. It's building the image. It's drawing it for me. It's converting it to the right format. It's printing the letter that I did for me. And this is the important thing. What it's doing, it's taking the letter array. The letter array is what is actually what I chose. And it's feeding it, the letter array, it's feeding it to the model in order to ask the model, hey, model, what am I getting? Is it, what is the answer? So let's just run this to see how it works. So I'm running this crazy cell now with you. And it's asking me to enter a letter. So let's start with, I don't know, let's start with B. Sorry. Okay. So look how nice it is. First of all, it drew B in the same format of MNIST. You see, it's 28 on 28, and this is B. Now let's look at the last layer, at the output layer, okay? After softmax, because I asked it to show me the softmax layer. And let's see, you see the biggest one is 4. If you look at the numbers, yes, see? It's 0.9. Which of course is the wrong answer, right? So the model is not really that great. Maybe we will improve it in a minute. But what you see here is I showed it deliberately. I put the model doesn't know whether it's a number. It just takes the number and starts running the neuron on it. And what this number told me, hey, the answer is 4, which of course is wrong. It's not even relevant. Let's do it again. Let's try now I. Maybe it will guess it's a 1. Let's hope it will think it's a 1. Okay. Yeah, see? It really thought it's a 1. And it makes sense because I looks like a 1. So you see that on the 1, we have 0.76. So it's the largest one in the softmax. Okay? And lastly, I want to show some other crazy things I asked DeepSeek to do. Let's go here, sorry.
How did it make the image of the letter?
Sorry, 1 minute. What's the question, please?
How did it make the image of the letter?
Oh, there's a code. I showed you the code. I'll be happy to show it again. Okay? It's just very simple code in Python. I'll show it in a minute. Okay. Okay, so what I did now, I asked, let me just minimize it for a second. So now I ask for another cell. I remember that the loss function that was chosen here was cross entropy. So I want now to be more flexible. Please add a cell which does the following. have the user input the loss function type. I want to choose the loss function type. And then another one, ask the user to choose the activation function. You chose a ReLU, I want to put a sigmoid. And then plot the loss function for each configuration. So what we're going to do now is we're going to take the model, okay? And we're going to just decide on what the activation functions are and what the loss function is. Okay, so let's run it. Okay, you see it's very nice here. It's already preparing the options. Sparse categorical, MSCs, the square, MAE, which I don't even remember what it is. And here you have three options for activation functions. Let's run this. Okay, so look how beautiful it is. It's telling me select a loss function. So I want to select mean square. And let's actually change this to, I don't know, sigmoid and train the model. Okay, so first of all, you see that it did pretty good job. Still, the loss is relatively small. The loss is always going down. Remember gradient descent? How I proved to you that you will almost always go down with the loss because you're using derivatives. Let's do a different one now. Let's here put, and let's train it again. Okay, so now you see the orange one is the one with tan H, and you see that they're very similar, but the orange one is even better, is actually better. And let's also look at the original one. Let's compare. And actually, if I remember well, what we select was even better than the original one. Let's do a train. Okay, so look at that. The green one is the original one. And you see that the two that we chose actually gave, a lower loss function. But obviously it's not important because what I'm trying to teach you now is simply how to build a network and to go back. This is really the most important part. This is where DeepSeek decided on the architecture. And actually we can do an interesting trick here. How about let's add another layer. Just to show you how simple it is. I just decided now to add another layer. And I can, let's make it, I don't know, 80. Let's make it 4. Let's be really crazy. Okay, so what I did now is I added another hidden layer, which is really small. And let's see if it will have an impact. I don't believe it will have a great impact, but let's try. So now I'm running the network, the new network. See, it's doing 5 epochs. Okay. And you see that actually it's not very good. The error is really terrible. So adding that layer was not a brilliant idea. I think that if I added a bigger one, it would probably give a much better results. Okay, are there any questions? Actually, I owe an answer to someone that asked, I don't know the name, how it was drawing the image. So let me show you how. It's very, very, very simple. So what you see here, letter equals input. This is where I actually put the letter of the alphabet. See, it gave me a text, enter an uppercase alphabet, blah, blah, blah. Okay? And by the way, if it wasn't upper, it's uppering it using this function. So what happened here is I just put the letter. But as it was so rightly asked, there's a big difference between selecting a letter and drawing it on a 28 by 28 canvas. So this is happening here. Create a 28 by 28 image with a letter. So this is exactly the command that does it. And what you're seeing here is actually drawing the letter. Okay? And here I am actually converting it to MNIST, and here I am plotting it. So this is the plot of the letter. And the most important thing is the prediction. So what happened here is model prediction is really, it's the most important thing. After we trained the network, this is the time to test it. So what we do is we just put the letter array, which is this one here, and we predict. We do the feed forward with the right weights because we already trained the system. So what I would like you to do is take a look at this code, play with it. There are some very deep ideas that will help you to really understand how it works. And most importantly, I just want to show you how simple it is today with with minimal knowledge of Python to build a network. Actually, you can do it without knowing Python at all. You could just run it and that's it. But I think it's important for us to understand a little bit deeper what the model was doing. And as I said, again, there are three important commands. Here we define the model. Here we compile the model. And here we run the model. Okay? Let's do epoch of 1. So obviously the results will be really terrible now. It will be very fast because it's running only once. That's it. You see, it's a huge error. Okay, now it's a bad network, so the chances that it will, let's try to do the eye again and see if it will be able to know that it's a 1 as before. So let's run this. Okay. Now it's asking me to put a letter. Let's do the eye as we did before. Huh? Yeah, it was a 1. Even with one epoch, it was able to guess it's a 1. But, with a bit lower probability. Okay, so we did some serious things today. It's the first time we actually write an AI model, solve a real AI problem, doing it with the right, most modern tools. And I think this could be a good time for questions before we start to talk about the exercise, unless someone here would like to share the screen and show how they did the XOR problem using TensorFlow.
Can I ask a question about
Sure.
activation functions?
Sure.
You have so many different types of functions. You can do the sigmoid and ReLU and TAN and whatever. How do you decide which one is right? Or is it just trial and error?
It's a very good question. So first of all, there's a lot of trial and error, but since, for example, sigmoid will only give you from 0 to 1, it makes sense to use it when we did the XOR, right? Because with XOR, at the end, we only want 1s and 0s. So that would probably be a sort of an intuitive approach. But to be honest, in my opinion, it's more of a trial and error, unless you're a seasoned AI engineer with a lot of experience, and this is where you would get the intuition, like where your grandmother, you ask her for how do you say matkon? I forgot, for a cake, and many times you would say recipe, right? Put salt like this and some sugar like this, and that's basically what happens with very good engineers, very experienced. They just have the intuition on how to do it. Now, the good news is that the models today are very good at giving you the first guess. Even though they did a horrible job with the demo I showed you now, usually, if I would give them a more serious problem, you would see that they would usually choose, at least initially, a smart way of doing the activation functions. But one more thing, are you Sarit?
Yes.
One more thing, it's important to understand that many times you can have two different activation functions and they will both give a good job. They will both give a good loss function, perhaps with a very small difference. But basically, in most cases, most activation functions will do a reasonable job. Some of them will have the convergence very fast, and some of them will have a slower convergence. But basically, it's a lot of intuition and some experience.
Okay, thank you.
Sure. Any more questions? Does anybody want to share their screen?
I can share. I just asked him to solve the problem and
Let's see what they did. But show us the prompt. You have to show us the prompt also.
Okay, but it's Hebrew. It's written in
It
Hebrew.
doesn't matter. It doesn't matter. I know a bit.
Okay.
I think I have to stop sharing. So
This is the code he gave me.
I don't see your screen.
Just a second. Let's try again.
Okay, you can tell us in English what the prompt was. You don't have to show it to us. But by the way, okay,
I just asked him solve me the XOR problem in LLM, and he start.
Show me the code. Let's look at the code together.
Yeah. And then I told him, okay, it asked me how do you want to solve it, so I wrote TensorFlow and.
Beautiful. Let's stop here. Is there any way you can zoom so we can see better? Actually, I'm really happy that I asked you to do it because we're seeing something really beautiful. Okay. So first of all, on the first line where it says x equals np array, sorry, you see the input. X's are usually the inputs. So we have 4 different kinds of inputs, right? 0, 0, 0, 1, 1, 0, and 1, 1. And then on Y, you have the correspondent outputs, the true answers, the labels. Now look at the model. So it chose a sequential model. And interestingly, it had one hidden layer, but of size 4. Okay, if you remember, we did it size 2, and it was really a torture for the network. It worked something like 10,000 epochs in order to get something reasonable. Obviously, with 4, it will be better. You see, it also chose sigmoid, which makes sense. And then we have the model compile. That's the second important one. And the loss function, like we did, was binary cross entropy. And let's look at the model fit. It took 5,000 epochs. It provided the X and the Y, the input and the outputs, you know, the inputs and the labels. 5,000 epochs, and let's run it. Did you run it?
No, he just gave me
it's not that important. Actually, it gave you a results of a run, of a hypothetical run.
Yeah.
But you see that it gave pretty good results. The reason I think it gave good results with less epochs is because we had 4 neurons. When we put 2 neurons in a hidden layer, it was really a torture. I wanted to put 2 so we can all look at the analytical solution more easily. Okay. Thank you very much, Liron. And let's go back now and start to discuss the exercise. And I think that you were supposed to get a message from Yuval. Sorry. I'm also adding an exercise for biologists. I understood that some people were concerned about using linear algebra. So, you know, from my perspective, you can do what you want. Even if you're a physicist and you want to do the biology one, that's fine. If you're a biologist and you want to do the physics exercise, it's fantastic. If you do both of them, I'll actually be very happy. But what's really important, and I'm showing you a slide that I showed in the first lecture, is you have to understand that we live in a different world and it applies to the exercise. Okay, so we're not just like in the old days, in the Google days, our phone was just connecting to a cloud and we were trying just to get data. Now you have a brain. When you work on the exercise, you have someone almost on the level of Einstein sitting next to you and helping you with it. So what I'm expecting you to do in the exercise is to do almost research. Okay, so you can take my exercise, feed it into the LLM, which I'm sure many of you thought of that brilliant idea, and send the answer. But that's not what I'm expecting. What I'm expecting you to do is you will see that the LLM, whatever one you choose, it will start interacting with you and offer things and provide beautiful physics ideas. At least this is what I got with ChatGPT. And what I expect you to do is to be creative and to think of new ideas and new approaches. And that's what I'm expecting in the exercise. You know, don't just put it in the LLM and click enter. That's not what I'm expecting. So first of all, I want to explain what I'm expecting what is the model we're talking about. And I'll show you here an amazing Claude simulation that I did. This one took me a few prompts. It wasn't that simple, but it's pretty amazing. So what it's doing, it's taking, like in the exercise I gave you, it's taking a random walk of 5 sites. Here, I can select whether I want the random walk to start in the middle, like here, to be...
You have to share your screen.
Oh, I apologize. I'm sorry. It would be interesting if I would continue like that for 20 minutes. Okay. Okay, so this is the simulation. It's a Claude simulation. And the reason I'm showing it to you now is just to show you the environment, what in general I want you to do. So we have 5 sites. We have a random walk. We can decide where we want it to start. Here we have time steps. I can run it 100 times, but I can also go step by step, which is the most important thing. And let's start. Okay, so I have a 5 by 5. It's starting in the center, and let's do the first step. Okay. So the first step, it started here, right, in the middle. So now you have a probability of 1/2 to be in this side and a probability of 1/2 to be on this side. Let's do another step. Okay, so now we have 25% to be here, 50% to be here, another 25% to be on the right side. Let's see what happens now. Okay, let's do another step. That's interesting. First of all, you see that we get very different results now, and I want to explain what happened. What is the boundary condition? So the boundary condition here is called stay. Okay, a stay boundary condition means that when you hit the wall, you are not reflected violently. You have some probability to stay there, and 1/2 of it to move back into the middle. Okay, so you see that I had 25% here, but now I can. 1/2 of it is staying here, and 1/2 of it was added here. Maybe I'll show it. Maybe I'll show the other. We call this a stay boundary condition. Let's look at the more violent one, which I call the reflect. Okay. So I call it kick. Okay. So this one says the minute you hit the wall, I'm kicking you back. So let's look at this now. So I'm starting in the center. Here it's the same. Okay. Sorry. Let's do from the beginning. Reset. Step. Okay. So I have 1/2 and 1/2. Let's do another step. Now I have 25% and 25%, but look what happens now. This here will now be empty because it kicks everything to this node. So let's do another step, and you see now it's empty. And by the way, if I go more and more, please look at this. It's very important. You see something which is almost periodic here. Not almost, it's periodic. Okay? And this is something that you will see is extremely deep. So let me just give a hint of something very deep that's happening here. Let's say I started here. Let's look at the first time step. Okay, I have 1/2 and 1/2, and I do another one, and I do another one, and I get 1/2 and 1/2. Okay, so what I see here, that if I started in the middle, on the second stage, I will get 1/2 and 1/2. But, and now comes the deep question. What if this was my initial state? This can also be my initial state, right? I can have a random walk where 25% of the walker is on the right side, the other 25% on the left side, and 50% in the middle. That's a fair thing to do, right? So look what happens now when I do first step, when I do another step. I get again to the same place. So this is really weird from a physics point of view. Can anybody say what's weird about this? There's something very, something that should raise concern. We have two different initial conditions, very different, that take me to the same point. Right? I can get to this stage, the 1/2 and 1/2, if I start here from 1, or I can get it if I start like this, because the next step is also like this. So what we are seeing here is something which is, in a way, problematic in physics, is we have two different initial conditions that lead me to the same final condition.
But it's a private case of only 4 possible spots. If you take 20, so maybe it won't happen.
Maybe, as you said, maybe that's one of the things you're going to discover, Liron. Okay? But it's a great question, and that's exactly the kind of thing I expect you to do. Try to see whether it happened because it's a small network or not. I'll give you a hint, it's not. It could happen on a bigger network also. But let's explain on a bigger site, on bigger space. But I want you to try to explain to me, what does it mean that you have a system that two different initial conditions lead to the same one?
Does it have anything to do with the chaos problem?
Not directly, no.
It will have kind of a rhythm, like it will repeat itself.
Sorry?
It might have some kind of a rhythm, it will repeat itself.
Well, you know, in the exercise that I gave you, if you remember, I had a transition matrix, and the whole idea of the transition matrix was to bring you from one step to another. The reason all this thing is done, the way all this thing is done, is by a matrix. And then I asked you, can you invert this matrix? Invert, it means that you have a matrix which is almost 1 over the original matrix. Now, if you can invert a matrix, it means that you can go from the future to the past, okay? Because you can take the system after 20 jumps and take it to the 19th jump by multiplying it with the invertible, with the inverted matrix, okay? With the inverse matrix. But what we are seeing here is that it's basically philosophically cannot happen, because if you say that at time 20, if you say that, let's say time 17, I had two different configuration that brought me to the same one at time 20, then if now I'm going back from 20, 19, 18, 17, which one will it choose? So what you will see that in a situation like this, the matrix is not invertible, which is a sigh of relief. What it tells you, hey, Joshua, you caught me here. You found a system that by definition cannot be inverted. And what you see mathematically is that the matrix of this system here will have a zero determinant. Zero determinant means that you cannot invert it. Now, I would like to ask you an intuitive question. What you saw here is what happens when you have what I call the violent tick boundaries. What if I have a software situation like this? Okay, so let's do this. Let's now see if we have the same situation. Let's do a reset, and let's now run by steps. Okay. Interestingly, see what happens after a long time? Can someone try to explain? I'm reminding you that we have 5 sites on this array. Look what happens after 20 clicks. What is interesting about the probability to be in each one of the 5?
It's equal.
Beautiful. It equals, which means we have maximum entropy. If you do the entropy calculation here, you will see that the entropy is maximal in this situation. Okay, let's do something more interesting now. Let's make the network a little bit bigger. Let's make it 11. Okay, and I'm doing an odd number on purpose. And we can actually even, let's not put it in the center. Let's put it on the left. Okay. Okay, see, now it's on the left. And let's look at the system. Let's run the simulation. Look how beautiful it is. It started on the left. You see it's propagating. Okay, I did 20 steps. Let's do some more steps. Instead of 20, let's do 100. Sorry. So you see how nicely it is. It will be equal to 1/11, which is almost 10%. And that's maximal entropy. So let me give you some crazy tips about the exercise you're going to do. First of all, the invertible or not invertible matrix does not depend on the size of the matrix. It only depends on the boundary condition. Okay? If it's a kick or a stay. Another interesting thing that you will learn is that there is a difference between a matrix which is odd, like 11 and 5, as we had here, or if we do 4 and 8, and even. The networks behave different. Now, that really doesn't make sense from a physics perspective. You agree with me? Imagine that you have 2 billion and 2 billion and 1. I mean, the system must behave in the same way. And what you'll see is something very interesting. In small sites, like Liron said, if you have 4 or 5, you will see a difference in the behavior. But this difference will gradually disappear when the network becomes bigger. And lastly, before we go, I want to ask you a question about this vector. Maybe we'll go back to the 5 on 5. This is the exercise I gave you. It's a 5 on 5 matrix. And please remember that for each kind of boundary condition, you have 2 different matrices. So the 5 on 5 matrices will be different here with kick and different with stay. The matrices will be very different. Now, if they're huge, if they're 1 million by 1 million, you will see that the difference in them is negligible. But if they are in the order of 4 or 5, they look very different and they provide very different physics. Now, just last remark, which would be perhaps a tip towards your research. Okay. So this is the 5 on 5 matrix. And if you remember, you all guessed correctly that it will go towards gradually to 20%. And my question is, this vector, if you look at this as a vector, it's actually 1, 1, 1, 1, 1. You can have a normalization factor divided by the square root of 1 over the square root of 5, but that's not important. You have a vector which is 1, 1, 1, 1. How would you say this vector is related to the transition matrix?
It's an eigenvector.
Beautiful, beautiful. It's an eigenvector. And why? Because we see that every time I multiply the matrix with this vector, it stays the same. It's not only, what is the name of the student that gave me the answer? Who gave me the answer?
I gave.
You, but what's your name?
Here it's Maya. Okay.
Okay, Maya. So Maya, do you know what the eigenvalue is?
I guess 1.
Beautiful. So if you take this matrix, the transition matrix will have an eigenvector which is 1, 1, 1, 1, 1 with an eigenvector 1. And what it means that every time you try to do a transition, nothing will change because we are in maximal entropy. Right? So I just want to tell you this is the beginning of the iceberg in terms of what you can do with ChatGPT and this problem. I'm not expecting a PhD, but the more you do, the better it is. And remember, we are not in the old days. We're now in a revolutionary time in history where you have a physicist sitting next to you and guiding you with intuition and mathematics. You can invert a matrix in one click. You can learn about, the internals of the matrix, the spectrum, the kernel, whatever in one click. And I just encourage you to be as wild as possible with it. And lastly, I want to talk about the exercise for the biologist. It's very simple. And again, if physicists prefer to do it, I have no problem with it. So it's please provide a simulation of one bacteria performing chemotaxis near a food source. Okay, I'm reminding you, chemotaxis is a way for a bacteria to get food. And the way it does it, if it sees nothing, it goes a regular random walk. And if it feels a gradient, a change, it starts doing a biased random walk. Now, 2, please differentiate between temporal and spatial gradients. Now, usually when you say gradients, you're talking about gradients in space. Okay? But since bacteria is so small, even if it has 2 sensors on its both sides, the distance between these 2 sensors is so small that no gradient will be felt. You know that a snake has a tongue that goes like this. And the reason it goes like this is because each part of the tongue smells something different, and then it can tell the gradient. But the bacteria is too small for that, and for that reason, it's doing something different, which is called temporal gradient. Temporal gradient means it remembers what the value was now, it remembers what it was in the next step, and then calculates the gradient. So it's a temporal gradient. Sorry. Okay. Now imagine you have many bacteria in 2D space with a few food sources. So you just build an array. Trust me, the Claude will build it for you. Just build an array, a 2x2 array, and just place some food sources on this array. Now you have to ask Claude to give you a way to control the potency. Potency, it means how strong the smell is, how strong the food source is of each source. And what I'm asking you now to do, now show the time development of the system after a long time. Okay, so after a long time, what we expect to see is that most of the bacteria are gathered near the sources, okay, because they eventually found them. And lastly, what I'm asking is, can you explain the relationship to stochastic gradient descent? Now, don't be alarmed, but I want to explain. Gradient descent, we all know what it is. Stochastic gradient descent, maybe you can guess, is a way to improve gradient descent in a way that it maybe will not fall into local minimas. And again, ask ATFM, ask the friendly model, okay? What is stochastic gradient descent? Explain it to me. And you can even ask it, is it also related to chemotaxis and bacteria? I don't care. I want you to be researchers and to get to the right answers by just putting smart prompts into the LLMs. That's for me, the big delta that I hope I will be able to do with this course is prepare you to be the next generation of researchers. Everything is changing. We are going to do things completely differently. And both of these exercises you can see how it's done. What I will also do, okay, I think it's getting late, so we'll stop here. I'll send you this deck, and we'll be in touch next Tuesday, where we're going to have a lecture about ChatGPT, about philosophy, about intelligence, about consciousness. It's probably going to be the most interesting lecture in this whole course. So see you all Tuesday, and have a great day.
In Zoom or?
No, it's going to be in person. I'm going to be in the university. I'm traveling today back to Israel.
Okay.
Okay. Thank you all. Have a great day.
Thank you.
Thank you.
Thank you. Bye-bye.